Okay, so I finished last week with a summary of what happens when you have two independent random variables. And what we saw is actually it's very useful because it simplifies the math quite significantly. And so just reminding the summary we had last week, we had that if they're independent, the joint probability density function is equal to the product of their marginals, right? That holds for all x and all y. You had that if you have the expectation of a product of a function of x and a function of y, this is equal to the product of the expectation. The covariance was equal to 0, right? And we say if they're independent, the covariance is equal to 0, or the correlation is equal to 0, but the inverse is not necessarily true. It's not because they are uncorrelated that actually they are independent, right? So that was a very important point. And then we saw that if you have the sum of two independent random variables, this is actually the variance of the sum of two independent random variables. This is equal to the sum of their variance. And more generally speaking, if you have a linear combination of those two, you had this ax plus by, that's a square variance of x plus b square variance of y. Again, if they're independent, this holds. And then we played a bit with this notion of moment generating function. And we said that the moment generating function of a sum of two random variables is equal to their product. Right, and this is actually was quite interesting because we relate this to Fourier transform. And then by relating this to Fourier transform, we got some insight that if we actually do some form of product in the transform domain, that means actually in the direct domain, we do some form of convolution. And this is something we're going to see today, but using a different method. And then we played with conditional PDF, right? And we said that actually this is the conditional PDF of x given y is just equal to the margin of x, right? And that holds for all x and all y. And as a consequence, the conditional expectation is equal of x given y is equal to the expectation of x. Okay, so this is actually a summary of what we finished with last week. And one important notion as a consequence of this, especially as a consequence of using this relationship here, we said that if you have x and y are two independent random variables, and you're looking at, for instance, z is equal to ax plus by, where x is normal with a mean mu x and variance sigma x square, and y is also normal, mu y sigma y square. Then you have that this quantity here, z, is still normal distributed, right? This is still normal distributed with a certain mean that is a mu x plus b mu y, and you have a certain variance that the a square sigma x square plus b square sigma y square. Okay, so how did we show this? Is essentially by using this property of the moment generating function and the fact that the moment generating function uniquely identifies a probability density function, right? So this was a quite powerful tool. You have a linear combination of two normal random variables. This linear combination here is still normal distributed. Okay, so this is for two random variables. You can do this for n of them. So if you have n independent random variables, and you say each of them is normal distributed with a certain mean mu I and certain variance sigma I square, then you can also define if you have a linear combination of those, right, a weighted sum, essentially this is still normal distributed with a mean that is equal to the sum over I of AI mu I, and the variance is equal to the sum over I of AI square sigma I square. Okay? So you can show this exactly in the same way as what we did here, what we did last week. Okay? It also relies on essentially writing this. The moment generating function of a sum of n random variables will be equal to the product of the moment generating functions. Good. So you may remember what I was saying a few lectures ago when we were looking at binomial random variables. And what we did at that time was to say, well, if I have a binomial random variable with parameter n and p, right, n the number of trials, p the probability of success, right? X is looking at the number of success in n trials. And we found that expectation of X was equal to NP, and the variance of X is equal to NP 1 minus P. Actually, this one we proved it in the lecture by first finding the probability mass function of a binomial random variables and then computing its expectation by using the definition. This one, we didn't show it. I just gave you the results, but maybe it's something you have looked at in the class. Right, so what I will show you here is a different way of computing those two quantities, but in a much easier way than what we did earlier on. So this is the number of success out of n trials. So what I can do, I can write X as actually a sum of n random variables, where each of them is essentially telling me I have a 1 if I have success, and I have 0 if I have failure. And this comes with a probability P and probability 1 minus P, right? And if you sum those n, essentially indeed, sum those 1 or zeros, you're going to have the number of success out of n trials, right? Now this random variable here, this is called Bernoulli. So what I'm saying here is that you can write binomial random variables as a sum of n Bernoulli random variables. Now all those x here, they're all independent. Right? So if we want to calculate expectation of x, what we're going to have is just a sum of the expectation of xi, right? And what is the expectation of xi? Is 1 multiplied by p plus 0 multiplied by 1 minus p. And so this is equal to p. So what we have here is simply np, right? Just in one line, you can find this, while it took us a number of lines earlier on in these modules to find it, right? So this is quite useful. What about the variance? Well, the variance is the same thing. You can say the variance of x, they're all independent, right? So that's going to be the sum over I or the variance of xi. And so what we need to calculate is the variance of xi. So what is the variance of xi? I'm going to have 1 minus its mean square multiplied by the probability of success plus 0 minus its mean square multiplied by the probability of failure here. And you can compute this, and what you get is 1 minus p multiplied by p. Right? So here you essentially get n times p 1 minus p. Okay? So, so this is just to show you a different calculation of a result that we have actually obtained earlier on, but this calculation is essentially much faster because we just rely on breaking a certain random variable, here this binomial, as a sum of Bernoulli. Good. So, so with this, we are almost done with this part. What I want to look at is the last part here, chain of random variables. But before going into that, I want to show you a few exam questions from previous years. Yeah, let's do this one. Not to scare you, but actually this was one question I was a little bit surprised. So let's look at the second one there, where we say consider the following statement, where we have two normal random variable, x1 and x2, and we say they're independent, and we say, well, 2x1 minus x2 is normal distributed with a certain mean and a certain variance. Is the statement correct? If yes, provide a proof. If not, correct the statement and provide a proof. What do you think? Correct? Not correct? Yeah?
Isn't it correct? It just follows what we just did.
Yeah, exactly. We just followed what we just did. So this, obviously, this is correct. This is not correct, right? You should have 4 sigma 1 squared plus sigma 2 squared, right? Now, what is the problem in that question is that probably 95% of the students just computed this and computed that, but did not show that actually this is still normal, right? So I'm stressing this again. The question here is that you have two normal random variables, and you have a weighted sum of them, and this is still normal with certain mean and certain variance. I'm not asking to find that the mean is indeed equal to that, and the variance is equal to that, right? Okay? So this is something that actually I was a little bit surprised when I asked that question a few years ago. And this is simply a direct application of what we have done. You can start with the moment-generating function, right? You can derive the moment-generating function for Gaussian random variables. And then you use the property that are independent. So the moment of weighted sum will be equal to a product of moment-generating function. And since the moment-generating function uniquely identified distribution, actually, you can show actually this is normal. Okay? So I just want to make sure actually this is okay, because it was not okay a few years ago. Okay. Good. So with this, so this is normal distributed, 2 mu1 minus mu2, 4 sigma 1 squared plus sigma 2 squared. So with this, let's move on to change of variables. And this is something that we have played with a little bit already. Yes?
So again, in order to prove the second statement, shouldn't we actually calculate it?
Yeah, so the first part is actually compute the moment-generating function of a normal random variable.
No, I mean to show that it's 4 sigma squared plus.
Oh yeah, you have to show. I'm not doing it there, but I mean it's exactly what we did last week. Yeah. So if you just do this, you don't prove anything, right? So it's exactly what we did last week. The moment-generating function of this will be essentially you're going to have the product of the moment-generating function of this and this one evaluated at a certain value of t, right? And then from there, you can use the expression that we have from here and then show that it's still normal, exactly following the steps that we did last week. The difference was we did with A and B. Here you just have 2 and minus 1, right? So some of those questions, we will go back to it in the revision sessions, and we'll cover different type of questions to make sure actually you grasp the kind of question that you may expect. Okay, so let's look at change of random variables, and this is something we played with a little bit in the context of one random variable. So we had a random variable x, right? and we were interested in another random variable that was g of x, right? And we had a certain, let's say, probability density function here, and we were interested in that probability density function, right? And so we use this. For instance, we had, I don't know, y is ax plus b. We use this, for instance, where we wanted to go from a standard normal random variable to actually a general random normal random variable. Okay, so what if now I have the following. I have two random variables, x and y, and now I create another one, z, that is a function of x and y. And so I know, for instance, the joint PDF of x and y, and what I'm interested in is the PDF of z. Okay? So let's look at some examples, some cases. So the first one that we can look at is, let's imagine that our function g is maximum between x, y. And let's imagine that x is exponentially distributed, parameter lambda, and y is also exponentially distributed with parameter lambda. And on top of this, we're saying that x and y are independent. Right, so I have two random variables, but now I'm looking at a new random variable z, and I'm interested in what is the PDF of z. So what can we do? Well, we can use what we have done so far, which is starting from the CDF of z, and from there, try to find the PDF of z. So what we can write is the probability that z is smaller or equal to this. This is the CDF of z evaluated at z. This is a probability that the max of x, y is smaller or equal to z, right? Now, if the max of those two random variables is smaller than something, that means that x has to be smaller than something and y has to be something than z, right? This is end, right? Now, we know that actually we have independence, right? So if we have independence, this is the definition of independence. This is this multiplied by that, right? And now we know that actually those two are exponentially distributed. So I know that f of x is lambda e minus lambda x for x positive. Otherwise, it's 0. And if I'm looking at the CDF of x evaluated at u, this is 1 minus e minus lambda u for u positive, and then otherwise it's 0. Right, so I can use this here, and what you get is 1 minus e minus lambda z square for z positive, and otherwise it's 0. Right, so this is a first step. Second step, same as what we did in the past. We take now a derivative of this CDF. And so what we obtain is 1 minus e minus lambda z multiplied by the derivative of that function there, lambda e minus lambda z. Z positive, otherwise is 0. Okay, and with this, you essentially obtain here the PDF of this new random variable z, that is the maximum between two exponentially distributed random variables. Right? Now, where is this used? This is used actually in practice. If you have a communication systems where you have a transmitter, you have a receiver, and the receiver is equipped with two antennas. This is what you have in your phone. And what's happening is that actually the data you transmit here is received at two different antennas. And what the receiver does here, by doing max, it tries at every time instance to use the antenna that actually has the highest signal power. So you have the signal that is obtained on two antennas, and the receiver, what it does is just select the antenna for which the signal power is actually the largest, right? And so actually this is used to design communication system. This is what you have, actually basic techniques that you have in 3G. And this was the motivation behind that question, exam question in May 2014. It was essentially computing. You have a communication system, so you have to compute a certain probability density function and compute some error probability. So it's actually a communication questions, but you don't have to know anything about communication. You can just think in terms of probability, right? That was really an application of probability in communication. Okay, so this is an example where we go indeed from two random variable x, y into to another function, another random variable z that is a function of those two. Let's look at another case that relates to what we looked at last week. So let's imagine that node z is the sum of two random variables. Right, and what I'm interested in is what is the PDF of z, right? So how are we going to solve this? Same trick, I start with the CDF of this random variable. So this is the probability that x plus y is smaller than z. And now I'm not saying anything about x and y, right? I'm just writing this in a relatively general manner. I'm saying that this probability can be defined now as an integral over a certain domain of a joint probability density function. And this domain here is such that this is valid. So what that means is that you have here x plus y has to be smaller than z. So if I integrate x between, if I integrate y, let's say between minus infinity and plus infinity, if I fix a certain value of y here, x will have to go from minus infinity all the way to z minus y. Okay? So I'm looking at this area here. Right, so essentially this is my joint probability density function. I'm integrating this over the domain that I'm interested in. Right? And now what we can do is, well, we can compute the PDF, and so that's the derivative with respect to z of now this quantity. Right? That looks really ugly. You have to take a derivative of a double integral. Right? So how do we do this? We go back to something we have used already. We use Leibniz. But a slightly more general version of what we have used. So Leibniz differentiation rule. What it says is that if you have a function of a certain quantity z, and this function is actually written as an integral where the two boundaries are a function of z of an argument that can also itself be a function of z. So you have z here, you have z there, and z there. And what you're interested in is to compute the derivative with respect to z of that function. So we have done this before, we have used this, but in the case where actually the argument here, the boundaries were function of z, but not the function itself, not the argument here. Right, so how do we do this? Well, Leibniz says actually you can take the derivative of the first boundary with respect to z, and you evaluate h as at this boundary, b of z, z. Then you do minus d at the lower boundary, h of a, z, z, and then you bring inside the integral the derivative of h. So you have a, z, b, z, and you take the partial derivative of that function h with respect to z. Right? And this is what we can use now. So we can actually apply Leibniz twice because we have two integrals. And so I can distinguish the two, but I have one integral here, and I have the outer one, right? So let's look at that. So if I take the derivative of this, right, what do we have here? You see that those boundaries are just constant. They're not a function of z, right? So when I will take this term, this derivative of infinity with respect to z, that's 0. Derivative of a of z with respect to z, derivative of infinity minus infinity with respect to z will be 0. So I'm going to have 0 minus 0. Then what do we have left is essentially bringing this derivative inside that integral. So I have plus integral between minus infinity and plus infinity of the derivative of this. And what is our h here? Our h is this red integral, right? So it's the derivative of minus infinity dx, and I have dy there. Okay? I'm applying Leibniz once, right? So I have essentially this term here is what we have there, right? Now we can apply Leibniz a second time. So I have 0 plus integral minus infinity plus infinity. What do we have? Apply Leibniz. I have the upper boundary is a function of z, right? So I have here derivative of this with respect to z, that's going to be 1. So I have 1 multiplied by the function here evaluated at this upper boundary. So fxy evaluated at x is now given by z minus y. So x takes the value of z minus y, minus the derivative of this lower boundary with respect to z, that's 0, plus the integral between minus infinity and z minus y of the derivative of, with respect to z, of this joint PDF. What is this? This is 0, right? This is not a function of z. Derivative will be equal to 0. And so what I'm left with is the integral between minus infinity and plus infinity of the joint PDF of xy evaluated at z minus y, y dy. So what's happening if they're independent? If they're independent, what do we get here? Integral between minus infinity and plus infinity of f of x evaluated at its argument here, z minus y, multiplied by f of y dy. Is that something you're familiar with? Imagine your y is some time and your x is some tau. Right? What is this? So this is only if you have independence. This is essentially the convolution of x with y. Right? You convolute the two functions. Right? So you convolute the two probability density function. Is that surprising? Well, it's not based on what we discussed last week. We said already last week that if you have two random variables x and y, we saw that actually the MGF is of that sum is actually a product of the MGF. So you can think of MGF being a transform domain. So if you multiply in a transform domain, you convolute in the direct domain. So this is essentially what we do here. You actually convolute in the direct domain, and the direct domain here is actually the PDF. Transform domain is the moment generating function or the characteristic function. Okay, so let's look at just an example of this. And so just to answer the question you asked me last Friday, if you have if you have x and y are now normal random variables, but they might be correlated, and you're looking at what's the PDF of that sum, you can reuse exactly this. You don't use that because they are not independent, but you can start with that. And this one, you know it. You know the joint PDF of two normal random variables with any correlation. That's this big expression I gave, right? So actually, it's a matter of computing that equation. Right. Good. So let's look at just an example, and actually, it's something reminiscent of some calculation you have done in linear systems. Let's imagine that I have two independent random variables, x and y, are independent, and x and y are actually exponentially distributed with parameter lambda. And what I'm interested in is z is equal to x plus y. Right? So we can look at the PDF of z as what? As an integral between minus infinity and plus infinity of what we have here. Of what we have exactly here. So this is f of x z minus y multiplied by f of y dy. Right? And so what is f of x here is lambda e minus lambda x for x positive, otherwise is 0. And f of y is the same thing for y positive, and otherwise it's 0. Right, so if you plug this into here, what you get is essentially now the integral between 0 and z, and you assume z is positive, of lambda square e minus lambda z minus y exponential minus lambda y dy. And otherwise, you have 0. Right, so what you do here, essentially you do a convolution. You have that term is something that looks like this, right? That term here is something that looks like this, right, with z. And you multiply the two and you integrate between 0 and z, right? So this is actually something you did in linear systems, convolution of two exponential functions. Okay, and so you can compute this. So if you do that, you get something that looks like z lambda square e minus lambda z. And so what you see here is that if you have two exponential random variables, they're independent, you take the sum of those two is actually not exponentially distributed. Right? The normal one was actually exponentially distributed. If you have the sum of two normal random variables, they're independent, the sum is still normal random variable. Here's an example where the sum of two exponentially distributed random variables is not exponentially distributed. Right? So the distribution can change because of the effect of the sum. Good. So so this is when we go from two random variable x and y into one random variable z, right? What if we want to do something a bit more complicated than that? What if we want to go now from two random variable x and y to two other random variables u and v? Right? So rather than going from 2 to 1, we go from 2 to 2. Right? So how can we solve this? Well, we can, under two conditions, if we have a clear relationship between those, and I can write u is, for instance, r, a function r of x and y, v is a function s of x and y, right? If I can invert that relationship so that there is a one-to-one relationship between x, y, and uv, so if I can write the opposite and say x is a function L, let's say for u and v, and y is a function t of u and v. So I just invert the relationship. So this is the first condition. The second one, so that means actually you have a one-to-one correspondence between x, y, and uv. And the second one, if the determinant of the Jacobian of that transformation is non-zero, then you can compute this. So what that means is that what is our Jacobian here is dx du, dx dv, dy du, dy dv. If this is non-zero, so if you have those two, then the joint probability density function of uv will be equal to the determinant of this Jacobian, and you take the absolute value multiplied by the joint PDF of x and y. Right, so this is reminiscent to what we have done earlier on. This is reminiscent of the expression I wrote earlier a few lectures back when we were saying the following, and we have used this quite a bit. Remember when we had a one-to-one relationship between x and y? Well, in that case, we had one random variable x all the way to y. Here we have now x, y all the way to uv. Right? So this is actually a more general form than this one. Right, so let's look at this. Where can we use this? For what kind of scenarios can we use this kind of relationship? So let's imagine I will give you two examples. The first one is, let's imagine I have x is exponentially distributed with parameter lambda equal to 1. Y is also exponentially distributed with parameter lambda equal to 1. And I'm saying x and y are independent. And I'm interested in a random variable u that is equal to x divided by x plus y. Right? And so the question is, what is the PDF of that new random variable, the ratio between two random variables? Right? Now you may say, what's the relationship with what we just talked about? Here we talk about x and y going into uv. Here I have x, y going into only one random variables. Right? So this relationship here can be useful because to solve that problem, you may actually introduce an auxiliary variables. And so what you may want to do, and that's what we're going to do here, we're going to go from xy into, so the joint PDF of xy into the joint PDF of fuv, and we're going to introduce an auxiliary random variable v, and from there we're going to compute the probability density function of u. Right, so what can we introduce here? There are multiple things that we could do, but what we could do is say, let's say u is x plus y, and v I can take equal to x plus y, just the denominator here. Right, so if I do this, that means actually x is equal to u multiplied by v, and y is equal to v minus x, it's equal to v minus uv, or v multiplied by 1 minus u. Okay? Now, one thing that you note here is x and y are always positive, right? You're interested in the positive part. So actually, v will actually be positive. So you're going to have realization of the random variable v will be positive. Realization of u will be always between 0 and 1, right? Could be 0 and 1 here. Because you're just looking at a ratio. And actually, it will be even strictly larger. Right, so you have this. What can we do now? You have two random variable x into two random variable xy into uv. So what we can do is we can compute the determinant of the Jacobian. And what is this? Is the determinant of dx du, dx dv, dy du, dy dv. So that's the determinant of dx du, that's v, dx dv, that's u, dy du, that's minus v, and dy dv is 1 minus u. Right, so this is equal to v multiplied by 1 minus u plus uv. This is equal to v. Okay? So the determinant of J is equal to V. It's actually indeed is positive. V is always positive. So now I can write the joint PDF of UV is equal to the determinant of J, absolute value, multiplied by the joint probability density function of X and Y. This, how can we build this when we know that actually that both exponentially distributed, they're independent. So I can write fx of x is lambda e minus lambda x for x positive. F of y is lambda e minus lambda y for y positive. And so this quantity here will be lambda square e minus lambda x plus y. Right? Just the product of the two because they're independent. Right? Now x plus y, we saw it here, x plus y is v. Right? So essentially what I have here is v multiplied by lambda square multiplied by e minus lambda v. Lambda square is equal, lambda is equal to 1. Right, so I can remove the lambda here and I have v multiplied by e minus exponential of minus v. Right, and that's for v positive and for u between 0 and 1. And otherwise, I have 0. Okay, you can do the same for lambda different than 1, right? You get a similar expression. You just have the lambda into this relationship, right? So now you have the joint PDF of uv that is given by this, and then from there you can compute the margin of u, right? That's the integral of the joint PDF of uv over v. What is v? V is positive, so between 0 and infinity. And if you integrate between 0 and infinity, v e minus v dv, what you get is 1 between 0 and 1. And otherwise, it is 0. Okay, so what you see here is actually the PDF of that ratio here is actually uniformly distributed between 0 and 1, right? If you want to get the margin of v, for some reason you're interested in this, you take the integral between 0 and 1 of v e minus v du, and what you get is v e minus v for v positive and otherwise 0, right? And as a side result, what you see here is that actually u and v are two independent random variables, right? The joint PDF of u and v given by this is indeed equal to the product of the two marginal. Okay, so I was interested in a random variable u, the PDF of a random variable u, and to get to that, we actually have an intermediate step that say, well, let's introduce an auxiliary random variable v. Let's do a change of random variable from two random variable x and y to u and v. And once we have this joint PDF, I can compute the marginal f of u. Okay, so this is one example where actually having a 2 to 2 relationship is actually very helpful. And introducing an auxiliary random variable is helpful. Okay, so this is one example. Is that clear? Yeah? So let's look at another example. Where I have two random variable x and y that are normal distributed with a mean 0 and a variance sigma square, and both of them are independent. Okay, and what we're interested in is this. Square root of x squared plus y squared. Right, so that's something that actually you may, in your mind, you may think about something. This resembles something like this. You have x, y, and then what you're looking at here is you have a certain point here. What you're looking at this is actually u is here. so the magnitude of this, right? And so if I'm interested in finding the PDF of u, what I can do is introduce another random variable, v, which is this angle here, which I call inverse tan of y over x, right? And essentially now I have the magnitude and the phase, if you like, or the angle and the magnitude, and I have a one-to-one relationship between x, y, and uv, and I can say x will be u cosine v, and y will be u sine v, right? And now we can do the same thing. If I'm interested in this, right, what I can do is first find a joint PDF, from there of xy, from there get the joint PDF of uv, and from there get the joint PDF, the margin of u. Right, so how can we do this? FUV will be again determinant of a Jacobian multiplied by the joint probability density function of xy. And so what is the determinant of J here? Is the determinant of dx du, dx dv, dy du, dy dv, and this is cosine determinant of cosine v dv minus u sine v, dy du, that's sine v, and dy dv is u cosine v. Right, so what you get here is essentially u. Okay? This is something we have done already earlier on when we play with normal random variables, and we wanted to show that actually it's a valid PDF. Right, so now we can apply this. So what is this FUV? Right, and u is always positive, right, is essentially now u multiplied by the joint PDF of xy. So what is this? They're both normal distributed, so I have f of x is 1 over 2 pi sigma square e minus x square over 2 sigma square, right? I have a mean of 0, right, so I have no mu here. And fy is 1 over 2 pi sigma square e minus y square over 2 sigma square. And so what I have here, they're both independent, x and y independent, so the joint PDF is the product of those two. Marginal, I have 1 over 2 pi sigma square e minus x square plus y square over 2 sigma square. Right? And what is this quantity? X square plus y square. This is just u square here, right? So this is u square. And so what we get is 1 over 2 pi sigma square multiplied by u e minus u square over 2 sigma square, right? And this is for u positive, and v is just an angle, so it's between minus pi and pi. Okay, otherwise it's 0. Okay? So it looks like something Gaussian here, right? But you have a u here, so actually it's not normal distributed anymore. It's not normal distributed. So what is this? Well, from this now we have the joint PDF of u and v. I can compute the margin of u, right? So that will be the integral between minus pi and pi of this quantity here, u over 2 pi sigma square e minus u square 2 sigma square dv. And it's pretty simple. Essentially, the 2 pi will disappear, and what I have left is e as u square over 2 sigma square divided by sigma square, right? And this is for u positive. Otherwise, it's 0. Right? So that's the PDF of this new random variable here, right? It looks something like this. What is the PDF of v? Well, that's the integral between 0 and infinity of this quantity, E minus u squared, so 2 sigma squared, and now I integrate with respect to du, right, the other random variables. This is 1 over 2 pi, and I have now minus E minus u squared over 2 sigma squared between 0 and positive infinity, and this equal to 1 over 2 pi. So in other words, if I do this transformation, I have x and y actually normal distributed with a 0 mean and a certain variance, right? So the x dimension and the y dimension, they're actually identically distributed. They're both independent. So if you look at this, if you think about this in a complex field, x is a real part, y could be an imaginary part, right? And what you're looking at is essentially a change of coordinate. You go from Cartesian coordinate into polar coordinate, and you're looking at now the distribution of the magnitude of this complex scalar and the distribution of the phase, right? And you realize actually the phase is uniformly distributed. And the reason for this is because you have Gaussian in x, Gaussian in y, so you have something that looks perfectly symmetric, right? So the phase will be actually uniformly distributed, but the distribution of the magnitude is not normal distributed. This is what is called, Rayleigh. So this is, U is actually a Rayleigh random variables, and this is actually a result that actually is used a lot in communication, signal processing, and other fields, is because we often play with complex Gaussian random variables. Okay, is that clear? Right, so these are two examples for you to understand a little bit how we do those change of random variables. And this is this Rayleigh distribution actually is a link to exponential as well. You can show that an exponential is actually the square of a Rayleigh random variable, but we will not go into those details. So this is used in communication a lot to actually model if you have a transmitter and you have a receiver and you look at the distribution of the magnitude of the electrical field or electromagnetic field that you have, that you receive at the receiver, is actually, you can show actually, is Rayleigh distributed. Right? So if you take wireless comm course in the 4th year, you will see how we can use that. Okay, so with this, let's have a break of 5 minutes now, and then we're going to continue with the last part of this section. Okay, let's resume. So just to clarify one thing here, so you see that actually if you multiply this by this, right, you get that, right? So that means actually the magnitude and the phase actually independent from each other. So you have x and y are normal distributed, they're independent. You can view this in a complex field. One is a real part, y is the imaginary part. They're both independent. If you look at this in the polar coordinate, you look at the magnitude and the phase, the two of them are also independent. Okay. Good. So let's look at two well-known theorems in probability. One is called the law of large numbers, and the other one is the central limit theorem, right? So let's imagine that we have n random variables, x1 all the way to xn, and they are independent. As you can see, we like independent random variables, makes our life much easier. They have a certain expectation that is the same for all of them. and they have a certain variance, sigma square, that is the same for all those n random variables, right? And what we're interested in is two quantities. Is first the sum of x1 all the way to xn, and the second one is the average, which is x1, I sum all the way to xn, and I divide by n. So it's the average of those n random variables. This is called, and we're going to use this later on, this is called sample mean in statistics. Right, so what I want to do here is I want to try to understand what's happening to those two quantities, s and x bar, when n grows, right? So the first thing we can say for finite n is expectation of s. What is it? Should know by now. Right, so they're all the same, they all have the same mean, so A is n mu. What is the variance of S? Yes, because they're all independent. Right? Expectation of x bar, this is again, that will be n mu divided by n, that's equal to mu. Right? So I hope we all follow here. And the variance of x bar, this will be 1 over n squared plus variance of x1 all the way to variance of xn. Right, so that's equal to n sigma square divided by n squared. This is sigma square over n. All good? Okay, so what does the law of large number tell us? Well, essentially it says that if you look at this x bar quantity, x bar converges towards mu in the limit when n goes to infinity. So that's what the law of large number tells us. So if you have this quantity here, which is simply a kind of average, you sum n random variables, you divide by n. Well, as n grows, essentially that quantity tends towards the true mean, the true expectation of each of those random variables, which is mu. And so more formally, this is actually a convergence in probability, which says that if for all epsilon positive, the limit when n grows to infinity of the probability of having x bar minus mu being positive, being larger than any positive epsilon, this is equal to 0. So it's a convergence in probability. There are different ways of defining convergences. But essentially, what we mean is that x tends towards mu when n goes to infinity. So where does that come from? Well, you can relate this to Chebyshev. So remind Chebyshev inequality, where we said if you have for all a positive, the probability of having x minus mu larger than a is smaller or equal to sigma square over a square, right? And so what we were looking at that time, you had a certain distribution. You have mu plus a, you have mu minus a, and you're looking at this probability here. And you're saying that actually this probability is always smaller than this quantity. No? So what we can do now is to apply Chebyshev to our problem. And so what we can write, I replace a by epsilon. I have for all epsilon positive, I have the probability of having x bar minus its mean, right? The mean of x bar is indeed equal to mu, minus its mean being larger than epsilon is smaller than the variance of x bar divided by epsilon square. What is the variance of x bar? Is what we did here. Is sigma square over n. So it's sigma squared over n multiplied by epsilon squared. And as n tends towards infinity, essentially this goes down to 0. Okay? So what that means is that actually this one, you can think about this as the variance of x bar is essentially a measure of, let's say you do some measurement, and you do the measurement n times, and you average those measurements. And so the variance of x bar here is a variance of the error that you have in the measurement. And the more you take measurements, essentially the more the variance decreases, right? And in the limit, that's why just doing this simple average or sample mean actually converge towards the theoretical mean. Okay? So this is used, actually, if you look at the 5G system, that is not deployed yet in the UK, as far as I know, but you have those ugly base stations I talked about a lot. You have those base stations, you have your mobile phones, and those base stations in 5G, they will be equipped with a very large number of antennas, hundreds of antennas. And so all the signal processing is done over a very large number of antennas, and because you have large number of antennas, you can think of essentially the law of large number kicks in the design of the system, because the number of antennas is essentially n here. You have large number of antennas, and each of those antennas is modeled as a random variable, and because of this, the law of large number kicks in, and that makes the design of the system simpler. Good. So this is about the law of large numbers. Another well-known theorem is CLT. So this is law of large number. And the other one is CLT, which is central limit theorem. And so what it says here is that if you have x1 all the way to xn, and here is a little bit, I make it a little bit stronger, the condition, they are independent and identically distributed. So they all have the same distribution fx of x, right? Maybe all normal, or all exponential, or all Bernoulli, whatever. Then what the central limit theorem says is actually if you take the sum of those n random variables, well, as n grows sufficiently large, this sum will behave as a normal random variable. So this will behave as a normal random variable with a certain mean. What is our mean is n mu. What is our variance is n sigma squared, because each of them here has a certain mean mu, and the variance xi is equal to sigma squared. Right? So this is a very qualitative way of describing it. It's not very rigorous. But this is the idea, is that you take a sum of random variables. They have to be independent and identically distributed. If n is sufficiently large, this will look like a Gaussian. Right? And this is the reason why the noise is Gaussian distributed. You can think of each of those x is the contribution of an electron. They all move independently from each other, but the sum of all those contributions actually becomes Gaussian. Right? It's beautiful, right? Yes?
Basically speaking, how many contributions do we expect for this to apply? Like obviously it can't be like 5 or 6. You have to take.
Yes, it's large. So it's, I mean, in the limit is up to the infinity, right? So, but you can compute. It depends on your tolerance. If you want to design a systems and you say, well, I have the variance. Essentially, you can compute the variance, and you can see that at some points it becomes more and more Gaussian. You can tolerate a certain gap. In some application, maybe with, I don't know, 100. In some other application, maybe much larger. It depends on what accuracy you need in the systems, right? But essentially, what is useful is actually it gives you a quite quick order of magnitude how to design how to solve a problem if you assume n is sufficiently large. Yeah.
In the previous theorem, is this intuition correct, the idea that we all have the same u, so we're trying to measure the same thing, and we're doing it many, many times.
Yes.
And so eventually, because we measure it many times, they're all measurements of the same thing, so that's why it's the same u. Eventually we get a mean that's quite close to the actual mean.
Yes, so the other one you can think of, you do a certain measurement, the same measurement but multiple times, but this measurement is noisy, right? And so if you did measurement only once, you may have some error. This is the variance of each of those random variables. But if you do the measurement multiple times and you average, the error of that measurement after doing this averaging actually is decreasing over time. Yes, so they're all centered around mu, right? But if you do the sample mean, so the averaging, actually the variance actually decreases, and in the limit when n becomes infinity, essentially it coincides into one single peak.
And for each one of them, like there's the highest likelihood is that we get the mean, but we probably won't get exactly the mean because it's distributed around it.
It's still distributed around this. So you have, let's say, if you look at xi, maybe distributed around, I don't know, mu is here, right? You may have something that looks like this, right? But if you now do x1 all the way to x10 and you divide by 10, what you will get is still, oops, sorry. So you still have mu, but you will have something that is much sharper, right? So that variance here, this is the variance of x bar. That variance here, which is the variance of xi, are different. And as you increase n, essentially that variance decreases. Right? Good. So the lower drummer is about the mean. The central limit theorem is about the distribution that is Gaussian. And so this is an example you can do on MATLAB. Where is it? Here. So you see here, you have, I'm throwing a die, and I have essentially 6 possible outcomes, 1 to 6, right? And I'm doing this many times, right? And so what you get is that indeed, the probability mass function, you see, is uniformly distributed, right? You do this 10,000 times, and so you're going to have 10,000 divided by 6 of 1, and then 1,000 in the limit where you actually do a large number, right? A large number of trials. And then this one here is when you take, you throw 2 dice, and then you sum the outcome, right? And so you can go from 2, because the minimum you get is 1 on each, all the way to 12, right? And you sum. And you see that actually you have higher probability of having 7, right? Because you can have 1 and 6, 3 and 4, and 5 and 2. So you have higher probability. And then you sum 3 of them. So you take 3 dice, and actually you sum 3 of them, the outcome of 3, but you do this many times, right? And you get something like this. And then you do this here 50 times, and what you see is that you get something where the envelope looks Gaussian distributed, right? Now, strictly speaking, this is not a Gaussian distribution because the outcome here is still discrete, right? So you sum, you have a discrete random variable, you sum n discrete random variable, the outcome is still discrete, right? So strictly speaking, this is not, you cannot say this is not continuous, right? But if you want to compute some form of probability, let's say the probability that x is smaller than something, then you can approximate this using Gaussian random variable, right? So this is what the central theorem says, actually more formally, is that if you have indeed x1 all the way to xn, they are IID, so independent and identically distributed, with all of them, the mean is mu, and the variance of xi, the sigma square. What do we get? What CLT says is actually the probability of having this sum of n random variables being smaller than something. So I'm looking at the CDF. This essentially can be written as S minus the mean of S, which is n mu, divided by the variance of S, here n sigma square. So I just subtract n mu and I divide by n sigma square. So here I have n minus n mu divided by n sigma square. Right? So far I don't use the central limit theorem, but the central limit theorem says that actually this is actually the same, or you can approximate this when n is sufficiently large, with the probability of having z smaller than a minus n mu divided by n sigma square root. And where z here is a normal, standard normal random variable with mean 0 and variance equal to 1. That's what it says. Right, so that means actually if you look at the probability of x being smaller than something, then you can use, if n is sufficiently large, you can actually approximate this using a normal random variable, and you can compute that probability using the probability of normal random variables, as we have done in the past. Okay, so this is useful because sometimes you actually don't know what's the distribution of each of those x. You know, it's just the same, right? But if you have sufficiently large n, then at some points you see that actually this will be Gaussian distributed, and that's why you can compute the probability using Gaussian random variables. Okay, so this is something you will see, you will play with. You have some more examples in the notes as well, if you're interested. But it's actually a very useful theorem because in many applications and in statistics as well, if you have a sufficiently large sample, or essentially you can use the central limit theorem and you can use a load of large numbers to simplify the calculation quite significantly, even though you may not know exactly how each of x is distributed. Okay, so let's move on to the last part of this, this module, which is about statistics. And you will see that statistics is not much different from probability. Essentially, all what we have done so far is will be actually used in statistics. So let's imagine that I'm doing some measurement, and for instance, I measured the value of a resistance. And the true value of a resistance, let's say maybe is 50 ohm. But when I do the measurement, I don't get 50 ohms. So I do a measurement once, and I get maybe 50.2 ohms. And then I do it once again, and I get, I don't know, 51. And then once again, 49.5, and then 48, and then 51.5, and so on, right? So I do this measurement here 5 times. So essentially, those values are just measurement, x1, x2, x3, x4, that I get after doing the measurement, right? So you can view this as actually sample data. Now, after doing the measurement, I know those values, but before doing the measurement, I'm not sure what value I'm going to get, simply because the measurement is noisy, right? So rather than measuring 50, right, which may be the values I want, actually, I don't measure 50, I measure 50 plus some noise, right? But the true value of 50, I don't know it. So what we do in statistics, as I explained earlier on at the very beginning of this course, you try to infer something about data that is now being corrupted by this noise. So I don't know actually its value 50, but what I measure is 5 different values of the sum of something that I'm interested in and some noise, right? Now, before doing the measurement, we don't know what's going to be the realization of that, the value we're going to get exactly. So essentially, all those x1, x2, all the way to x5 are just realization of random variables. So those are just realization of random variable x1, random variable x2, random variable x3, x4, x5. And each of them actually may be independent from each other, and they may be identically distributed, right? Good. So when we and so what we do in statistics, essentially, we try to compute some quantity based on those measured data. So one example of this is when we did this sample mean, we had x1 all the way to xn divided by n, right? Essentially, this is my sample mean. If I really evaluate this based on the data I have here, I'm going to have x bar is x1 all the way plus x5. Let's say I have 5 of them, right, divided by 5. So this will be actually a certain quantity that I compute based on those measurements, right? So what is this quantity? Any quantity that is calculated from sample data, and this is my sample data, any quantity that is calculated from is called a statistic. So this is and a statistic is nothing else than a random variable, right? Is any quantity that is calculated from sample data. Each sample data before doing the measurement actually can be viewed as a random variable. So essentially any quantity that is calculated from those random variables will still be a random variable. Right? You can view the statistic as just a random variable. And so because it's a random variable, any of those statistics will have a certain probability distribution function, or density function, or probability mass function. Now, how do we choose this sample data, or this sample? So this is an example, but in practice, what you want, as much as possible, because it makes your life easier, is to have what we call a random sample. So that means that all those random variables, x1 to x5, or in general x1 to xn, they're actually all independent and identically distributed. So they all have the same distribution, fx of x, right? But they're all independent. And so, for instance, they may all be normal distributed, right? Or it may all be exponentially distributed, whatever. If it's actually some form of Gaussian noise, maybe each of them here will be normal distributed with a certain mean and a certain variance, right? But the same distribution. Okay? But if it's a random sample, they all have the same distribution, but they're also all independent from each other. Okay, so what is the mu here in that problem? If I have Gaussian, if I have some noise, that mu here may be actually this 50. And what I experience is not exactly 50, it's something that is corrupted because my noise in this case would be, for instance, 0 mean and a certain variance sigma square. So the sum of this one and this one would still give me something that is normal distributed with mu, for instance, is equal to 50. But I don't know that exact value. Yes?
Why do you have multiple random variables instead of having one?
Because they all have the same in a random sample, they all have the same distribution, but they're all independent from each other. So all measurements actually independent from each other. So they have the same distribution, but the outcome or the realization of that random variable will be different at each realization. That's why actually we just consider having different and independent random variables. But they're the same in the sense that it can be the same distribution. If it's a random sample, it's the same distribution.
So the overall result is going to be another distribution.
So if you do a statistic, you take a statistic, so you compute something based on those data, the distribution of that statistic will depend on the number of samples that you have, and will depend also on that fx of x, so if it's normal or if it's something else. Right, so one statistic could be, for instance, the sample mean, so the one we just seen here, right? So my sample mean is a statistic, is a quantity that actually I calculate from sample data, and we have seen this already, that actually expectation of this sample mean is mu, right? And the variance of the sample mean is sigma square over n. Right, so what you see here is that if you have x1 all the way to xn are all normal distributed, here, as we have here, they're all normal distributed, and they form a random sample, so they're all independent, right? For instance, I can compute this x bar, and this will be also normal distributed with a certain mean mu and a variance sigma square over n. Right? Can you see? Yeah. right? So this is essentially what we have done earlier on. I just have n random variables. I sum them up. I divide by n. And so what I have is actually a statistic that has a certain distribution that is still normal in this case, with a certain mean and a certain variance. And so as I increase n, essentially, my measurement on the error essentially is decreasing. And so I have that actually this sample mean or this average is essentially more accurate than each of those underlying realization, right? Exactly that's what we have seen in the law of large numbers, right? So this, if they're all normal distributed, actually the sum is still normal distributed. Well, if they're not normal distributed, they're distributed differently, but if n is sufficiently large, then you could still say that actually that sum will be normal distributed using the central limit theorem. Right? So what do we want to do with this? What do we want to actually compute in statistic is essentially we want to infer, we may know it's normal distributed, but we don't know what is this mu. We don't know what is this sigma square. So in this example here, we don't know that actually the true value we're looking at is 50. What we just observed is 50.2, 51, 49, and so on, right? But we want to take multiple data, multiple samples, sample data, in order to try to infer something about the properties of this underlying distribution. So it may be normal distributed, but we have no idea what's the true value of mu and what's the value of this sigma square. So we want to actually build estimators and estimate of those quantities. Right, so let me give you some example here. So if I have that fx is maybe normal distributed, mu and sigma square, what I may be interested is an estimator of mu. And so this is what we called mu hat, for instance, or an estimator of sigma square, sigma hat. So what is this? What is an estimator here? Is just a statistic. It's just, again, a random variable. It's a quantity that you compute based on some data, but that you'll try to design in such a way that it gives you the best estimate of the value that you're looking at, right? So for instance, if I use the sample mean here, if I use x bar as an estimator, so my estimator of the mean, mu, for instance, I will have the estimator is x bar, which is the sum of all those n random variables, right? And what will be, so that's going to be my estimator, so it's just a statistic. What will be the estimate? My estimate will be essentially the value of x bar when I use the data that I have collected, so x1 all the way to xn, right? So in terms of probability, those are just random variables. They're just quantity that actually are function of the underlying random variables that you have here in your random sample, right? So if I want to estimate mu, so if I want to estimate this 50 here in this example, well, I could take, for instance, x1 all the way to xn. But I could take something else. Nobody says actually you have to take all those n data, right? I could take another estimator that could be, for instance, I take x1 plus x10 and I divide it by 2. That could be an estimator as well, right? And my estimate then would be x1 plus x10 over 2, right? So that's maybe option 1, and this could be an option 2, right? So 2 different estimator, and they would give me different values of what I'm looking at, right? Different values of this estimate of mu here, right? Now the question is, some of them can be more reliable than others, right? So we have to define some properties of those estimators. So if I want to identify what's the mean or what's the variance of this distribution of my sample, my random sample here, I want to define some actually kind of properties or that actually I can quantify to actually try to assess whether actually this is a good estimator or is a bad estimator. So one first property that we use a lot is the notion of unbiased versus biased estimator. Right, so what that means is that if I have something that is unbiased, if I have an estimator that is unbiased, right, so for instance, I have here theta hat is an estimator of theta, right? That example, I could have mu hat is an estimator of mu, so if I'm looking at the mu of here, and I want to build an estimator of that mu, I'm just going to denote it with a hat. So if I have an unbiased estimator, theta, what that means is that the expectation of theta hat is actually equal to theta. So that means actually if I have a certain value theta or certain value mu that actually I want to estimate, that may be the 50 I had in the previous example, I don't know that value. But I can say that using probability, I can build an estimator that maybe has this one. That estimator is a random variable, so it has a certain probability density function or probability mass function. And if the expectation of that estimator is equal to theta, then on average, it means that that estimator will give me the correct value. Right? So this is an unbiased estimator. So the bias, which is expectation of h hat minus theta, is equal to 0. If you have a biased estimator, it means actually the expectation of theta hat is actually different from theta. And so you have a bias that is different from 0. And so that means that if your theta is here, you have now a distribution maybe that is something like this, right? And the expectation of theta hat is different from theta. So that means that you have in this example here, you have 5 values, measured values. You build an estimator, so it's a random variable that tries to estimate that 50 that you're looking at, that you don't know, right? But some estimator, on average, may give you the correct answer. Some estimator may not give you the correct answer, right? And this is what is reflected through this notion of biasing, is that if you unbias, on average, that estimator will give you the correct value that you're looking at, or you're searching for, and otherwise you have a gap between the expectation of that estimator and the value that you looking at. Right, so what if we use X bar, so this sample mean, as an estimator of mu, right? So imagine I have x1 all the way to xn is a random sample, right, with a certain distribution f of x. And I have that actually the mean of those random variables is equal to mu, right? So that's what I'm saying here. I have a random samples and the independent and identically distributed random variables. I have a certain distribution which I don't know, but I don't know the mean, and I'm looking at an estimator to actually try to estimate that mean, right? So, and what I want to do here is use x bar as an estimator of mu. So x bar is x1 plus xn divided by n, right? If I take expectation of x bar, this is again the sum of expectation of xi divided by n. So this is n multiplied by mu divided by n. This is mu, right? So that means that if I have random samples and I use an estimator of mu of that mean, I use the sample mean. The sample mean is actually an unbiased estimator of mu. So x bar is an unbiased estimator of mu, the mean, the theoretical mean of the underlying distribution, right? So that means that if you have mu here, x bar will have a certain distribution with a non-zero variance, but its mean will actually be equal to mu. Yes?
So is this saying that if we took an infinite number of means with, like, say, an arbitrary number, a finite arbitrary number of samples, and we took the mean of those means, we would get the mean of these independent identity large numbers?
The means of those means. So you can view this once. Indeed, if you take n sufficiently large, what's going to happen here is actually the variance of that estimator will decrease, right? So in other words, the estimator, as n grows large, that estimator will give you, with higher probability, will actually give you the true values that you're looking at, right? So if you have this here, you have only 5 samples, or you have 500 samples, but for both cases, you use the sample mean, right, as an estimator of mu. In one case, you may have actually a variance that is like this. In the other case, you're going to have a variance that is much smaller. Right, I'm not sure.
If we were to fix n, and so keep it at 5, for instance,
Yeah.
and then we take the sample mean of those, we take multiple realizations of the estimator, the sample mean, with 5 each time. If we do an infinite number of those estimator realizations, their mean would be the mean of
Yes.
Whereas for a biased one, it would be some offset.
That's right. Yes. Okay, so this is the first one. Is actually the sample mean is actually an unbiased estimator of mu. Now, what if we want to look at the variance? So I want to estimate the variance of this distribution. X bar would be a good estimator for mu, but what about the variance? So what we can do is we can define also an estimator. Now call it S square estimator of sigma square. And I want to have this estimator to be unbiased. So how we're going to define S square is a little bit funny, but is 1 over n minus 1. And I sum here, I have something that looks something very similar to a variance. I have a random variable minus a sample mean, and I take the square of the deviation between xi and the sample mean. So x bar here, the sample mean, is not the same as the expectation of xi, right? It's not the same. You just here have an estimator of the variance of x, but you have to rely only on the data that you can measure, right? So I'm not writing here mu, I'm writing x bar because I don't know mu, right? So, and I'm divided by n minus 1. I'm not dividing by n. And the reason why we don't divide by n is because otherwise it would be biased. So we can show that actually this is an unbiased estimator of the variance. So how can we show this? I can say, well, this is 1 over n minus 1, the sum over n. And now actually I'm subtracting and adding mu to this quantity, so I don't change anything. But by doing this, we can show something interesting. So I have, I expand the terms now, so I have xi minus mu square plus sum I to n of mu minus x bar square plus 2 sum 1 to n of xi minus mu minus x bar. Right? So what can we say from this? Well, this one here, this is the same as mu minus x bar. I bring outside of the sum 1 to n xi minus mu. Right, so what can we say about this? This is n mu minus n multiplied by x bar. Right? And this is the same as n multiplied by x bar minus mu. Right, so this quantity here is 2n mu minus x bar minus mu. Are we all good? Yeah. So what else can I say here? This will be this is independent of n, so this is n times mu minus x bar. Right, so what we have is 1 over n minus 1. And I have a sum now, sum 1 to n of xi minus mu square. And now I have, what do I have here? I have, I can write this as minus 2n mu minus x bar square. Right, so here I have minus n mu minus x bar squared. Good. So what about expectation of x squared? If the expectation of s squared is equal to sigma squared, then s squared would be an unbiased estimator of sigma squared, right? So this is 1 over n minus 1. I have a sum I to n of expectation of xi minus mu square minus n multiplied by the expectation of mu minus x bar square. So what do we have here? What is this quantity here? I have xi, mu is the mean of xi, so this is the variance of xi. And the variance of xi is sigma square. So I have 1 over n minus 1, n sigma square minus. What do I have here? This is the variance. This is n, the variance of x bar, right? The variance of the variance of x bar. Let me write the expectation of x bar is equal to mu, right? So this essentially here, this quantity is expectation of x bar. Right, so I have the expectation of the square of the deviation between x bar and its mean. So indeed, this is n variance sigma square. Now, what is the variance of sigma square? This is sigma square. What is the variance of the sample mean is sigma square over n. And so what I have here is 1 over n minus 1 and sigma square minus sigma square. And this is indeed equal to sigma square. Okay, so this is this funny result that you have to divide by n minus 1 here in order to actually have this estimator to be unbiased. And so what that means that if you use s squared and you're looking at a certain quantity, you want to estimate the variance, sigma square, what you use is maybe s squared as an estimator of that variance. Well, expectation of x squared will be equal to sigma squared. So indeed, that estimator will be an unbiased estimator of the variance that you want to estimate. Okay, so this is not the only way to design estimators. So that's the notion of biased and unbiased. So one thing that is quite natural is that if you have two estimators that both unbiased, you may want to choose the one that has the minimum variance. So this is what is called minimum variance unbiased estimator of FMVUE. What that means is that imagine I have a certain estimator of theta. I have a first estimator that is this one, and I have another one that is maybe something like this. Right, so I have theta 1, that's the first estimator, and I have theta 2 hat, that's the second estimator. Right, I have two different estimators, and both of them are such that expectation of the estimator is equal to theta, expectation of the estimator of the second estimator is equal to theta as well. They are both unbiased. But you see that the red one has a wider, larger variance, right? So if this is the case, you want to choose the one with the smaller variance. You know that actually on average, both of them will give you the value that you're searching, but you have less deviation if you choose the one with the minimum variance, okay? So this is what's happening when you have unbiased estimator. Next week I will talk about the case where actually you want to trade the variance and the bias, and you can have some benefit in doing that, yes?
You said that we always have to choose the minimum variance, but what if the original statistics is represented better by the one with the larger variance?
No, so both of them here, so for instance in this example here, you know that both of them, for instance, those random variables are normal distributed. But you have no idea what's the mean and what's the variance. Yes, so you may know it's normal distributed, it may be exponential. There are some cases where you don't know, but in this case, you assume first that you know the distribution. So let's say you know it's normal distributed, you have no idea what's the mean and what's the variance, right? So in that case, you would say, well, I'm having an estimator of my mean, for instance, but it's an estimator, so it's still a random variable. So it's a random variable that tries to estimate a parameter of another random variable, right? X1 here is a random variable. It has a certain mean, and then what I'm creating is an estimator, which is another random variable, which estimates this parameter mu, okay? And what I'm saying is that if you have multiple estimators, they're both all unbiased, the one that you prefer is the one that creates the smaller variance. Okay? Good. I know there are lots of things to absorb. So I will stop here for today, and I will see you next Tuesday for the last lecture. Thank you.